In the last video, we introduced the process for solving force puzzles and introduced two forces, applied force and tension. In this video, we will examine the weight force, the normal force, and the spring force, and see more techniques for solving one-dimensional puzzles. Some forces are seen very commonly and have their own symbols. Even more interesting, these forces can be calculated from other quantities. You don't have to be told their values directly. For instance, this 2-kilogram coconut is falling from a tree because it feels a force of gravity from the earth. For this coconut, or for any object close to the surface of the earth, the force of the earth would be calculated from Newton's second law. The force of gravity is also called weight. We will symbolize it with a capital W with a vector sign. We can calculate the value of weight using F equals ma. It would work out to 2 kilograms times acceleration due to gravity, which on Earth is 9.81 meters per second squared. The size or strength of the force then works out to 19.62 newtons. Since acceleration due to gravity is used so frequently, especially in forces, we give it its own special symbol, the lowercase letter g. So the equation for weight is commonly written like this. Weight is equal to mass times gravity. W equals mg. Now be careful of one thing. Weight and mass are not the same thing. Mass is a measure of the quantity of matter within an object. Weight is a measure of the gravitational force on it. So for example, if you were in intergalactic space, far away from any planets or stars, your mass would still be the same as what it was on Earth because the amount of stuff in you has not changed. But your weight would be zero. You would be feeling no gravitational forces at all. Now we will see a case where we know the acceleration and need to solve for a force. The weight force will help us in this puzzle. Consider this puzzle. What force does the ground exert on a stationary 2-kilogram coconut? Let's use our process. First, we draw a picture. Second, we draw a free body diagram. Gravity always pulls the coconut toward the center of the earth. But if weight were the only force acting on the coconut, it would accelerate. It's clearly not accelerating, so there must be some other force to exactly balance out the weight and to make the acceleration zero. Whenever an object rests on a surface, it is experiencing a support force from that surface. This support force is called the normal force, and it is symbolized with the capital letter N. Unlike weight, the normal force does not have an equation. We have to deduce its size from other forces. But we can easily find its direction. It always points at right angles to the surface that the object is resting on. Here we can say the floor is pushing up on the coconut to prevent it from falling down to the center of the earth. Third, set origin and axes. We will set upwards as positive y. Fourth, find the total force on the coconut. The total force is composed of two forces this time. The normal force pointed up and the weight pointed down. Because they are in opposite directions, we take the difference. We symbolize this as follows. Total force equals normal force minus weight, or total F equals N minus W. Fifth, apply Newton's second. We set the total force, N minus W, equal to mass times acceleration. Sixth, substitute for all knowns. The mass is 2 kilograms. The acceleration is 0 because the coconut was standing still. But we know something more. Weight is given by the formula mass times gravity. Again, we know the mass, 2 kilograms, and we know g, 9.81 meters per second squared. So we can solve for weight, 19.62 newtons. Then we take that value of 19.62 newtons and use that in the force balance. We now have normal force minus 19.62 equals 2 times 0. Simplifying both sides, we find the normal force equals 19.62 newtons as well. We have now solved a puzzle where two forces point in opposite directions and one was unknown. Here we see two horses pulling on a cart. The horses are connected to the cart via ropes. Ropes introduce a new type of force called tension. Like the normal force and unlike weight, tension does not have a formula. The tension in the ropes are caused by the horses. This is what accelerates the cart from rest. Consider this puzzle. A 100 kilogram cart is drawn by two horses, each drawing its own rope. The acceleration of the cart is 1 meter per second squared rightwards, and the tensions in the two ropes are equal. Solve for the normal force on the cart and the tension in each rope. First, draw a picture. Second, draw the free body diagram. Weight points down, normal force points up, and the tension in each rope points rightward. I'll draw two tensions for two ropes and two horses. We'll call them T1 and T2. Third, set origin and axes. I will set rightwards as positive. Fourth, find the total force. This time we have forces in both x and y, so we have to solve these separately. For the sake of flow, I will completely solve things once in y and only then turn to x. The total force in y consists of two forces, normal pointing up minus weight pointing down. Step 5. We set the total force equal to mass times acceleration. Step 6. Substitute for all knowns. The normal force is unknown. But the cart isn't moving in the y direction. It is not falling towards the center of the earth, nor is it levitating off the surface of the earth. So the acceleration in y is 0. And we can solve for the weight of the cart using W equals mg. It works out to 981 newtons. We put this information into the force balance. Step 7. We solve for the normal force. A little algebra and we get 981 newtons. That accounts for the forces in y. What about the forces in x? Well, let's return to step 4. The total force in the x direction consists of two tensions, T1 plus T2. We add them since they are pointed in the same direction. Step 5. We apply F equals ma. That gives us T1 plus T2 equals mass times acceleration in the x direction. Step 6. Substitute everything that is known, the mass and the acceleration. Finally, step 7. Solve. The sum of the tensions is 100 I hat newtons. We were told the tensions are equal, so each individual tension is 50 I hat newtons. So the normal force is 981 newtons, and each tension is 50 newtons. We have now solved a puzzle where there were forces in both x and y, and two of them pointed in the same direction. You run into the normal force every day. For instance, when you step on your bathroom scales, the scales are really reading your normal force, even though it's in a different set of units than newtons. So far, we've seen cases where the weight force and the normal force are equal. But this doesn't have to be the case. For instance, if you're in an elevator, the elevator has to accelerate you from rest, and according to Newton's first and second laws, that means it has to apply a net force. Consider this question. You have a mass of 70 kilograms. You stand in an elevator. A. If the elevator accelerates you upward at 1 meter per second squared, what normal force must the elevator apply on you? We start, as always, by drawing a picture. Here's a fellow who is inside the elevator. Now, this person is subjected to two forces. There is weight pointed down, obviously, but there is also a normal force pointed up, and we know this because our character is supported by the elevator floor. The normal force might look something like this. As always, we set our origin on the spot itself, and we set upwards as being our y-axis. Now, let's examine the forces that are taking place in the y direction. The total force is given by normal pointing up minus weight pointed down. I will write it as normal plus weight on the understanding that weight is a negative force. Now, we know that total force is equal to mass times acceleration. That's Newton's second law. So now we'll put these two equations together. Normal force plus weight force is equal to mass times acceleration. Now the problem we run into is we don't know what the weight force is just at this moment, so we need to calculate that out. Let's start. The weight force is calculated as mass times gravity. The mass is 70 kilograms times gravity, which is 9.81 meters per second squared. So 70 times 9.81 gives us 686.7 newtons. So this has now calculated for us what the weight force is. We take this and we plug it in for weight over here, again remembering that the weight is negative. So we can now say that the normal force minus the weight force of 686.7, or if you prefer I could say plus negative 686.7 newtons, is equal to mass, which was 70, times an acceleration. The acceleration of our character was upwards at 1 meter per second squared. So we now have normal minus 686.7 is equal to 70. So all we have to do now is to add 686.7 to both sides, and we end up with a normal force which is equal to 756.7 newtons. And to be clear, this is now in the j-hat direction. So here's the situation where the normal force is greater than the weight force, and we need it to be that way in order for our character to accelerate upwards at 1 meter per second squared. By the way, you would actually see this in an elevator. A set of balance scales would indeed display an increase in normal force as you accelerate upwards. What about part B? If the elevator accelerates you downward at 1 meter per second squared, what normal force does the elevator apply on you? For this latter part of the question, you can probably imagine that it would be solved very similarly to the earlier part. But just for the sake of getting some practice, let's draw it out in full. Here's our character in the elevator. They're going to accelerate downwards at 1 meter per second squared. So the free body diagram for this person would look as follows. They would have the weight pointing downwards, and they would have a normal force pointing upwards. Free body diagrams don't need to be to scale. They just need to show where the appropriate forces are. So here is the origin. Again, it's always put on the spot. And again, I'm going to set upwards as being positive. Now, let's look at the forces occurring in the y direction. The total force is equal to normal plus weight, on the understanding that weight is a negative force because it's pointed in the negative direction. But total force is also equal to mass times acceleration. So that means that normal plus weight must be equal to mass times acceleration. Now, we worked out the weight earlier, but again, for the sake of completeness, I'll work it out in full. Weight is equal to mass times gravity. Our hero has a mass of 70 kilograms, multiplied by a gravitational force of 9.81, or I should say a gravitational acceleration of 9.81. So 70 times 9.81 is 686.7. So now we take the 686.7 and we put it into this equation over here, this force balance. So the normal force plus negative 686.7 again, remember it's negative because this equation only gives us the positive value, the absolute value of weight, but weight is really pointed downwards in the negative direction, is equal to the mass, 70, times the acceleration. The acceleration is also downwards this time, so that means that it is going to be negative. So we now have normal force minus 686.7 is equal to negative 70. So adding 686.7 to both sides, we now have a normal force which is equal to 616.7 newtons, and it would be pointed in the j-hat direction. So this is an instance where the normal force is less than the weight force, and again, this is necessary if you want to have a negative acceleration.
And this is indeed what you see when an elevator accelerates downwards. In some cases, we need to use Newton's third law to evaluate the sizes of forces in a puzzle. Consider this common situation. A 3-kilogram book is on a table, and a 2-kilogram book is on top of it. Determine the strengths of all forces acting on each book.
So let's take a look at what a picture might look like. Here's a table. We have a 3-kilogram book, and we have a 2-kilogram book sitting on top of it. So we'll start by drawing our free body diagrams, plural, because we have two different objects. We have the 2-kilogram object, and we have the 3-kilogram object. Now, the 2-kilogram object is going to feel a weight pointed down. Nothing mysterious there. But it's also going to feel a normal force. And for reasons that will become clear, I'm going to draw this normal force in purple. Where is this normal force getting exerted from? From the 3-kilogram book. So the normal force is exerted by 3 on 2, not by the table. So this is now a complete free body diagram for the 2-kilogram object. It has a weight pointed down and a normal force from 3 pointed up. What about the 3-kilogram object? Well, the first thing that we can say is that since we know that there's a normal force of object 3 on object 2, then according to Newton's third law, there must be a corresponding force of object 2 and object 3. It must be equal and opposite. Because the 3-kilogram object is exerting a force on object 2, that means that object 2 must exert an equal and opposite force on object 3. And this is in addition to object 3's weight And this is in addition to the support that object 3 is going to feel from the table. This is the normal force that object 3 feels from the table. Now, let's put in our origin and axes. Because we have two different free body diagrams, we need to draw in two different origins and axes. So for the 2 kilogram object, I'm going to set my origin as usual at the spot, and I'm going to set my y-axis to be upwards. For the 3 kilogram, I will again set my origin at the spot, and I will again set my y-axis to be upwards. Now, let's analyze the forces occurring on the 2 kilogram object. The 2 kilogram object feels forces purely in the y direction, and the total force in the y direction is equal to the normal force of object 3 supporting it plus the weight force of object 2, on the understanding that, again, the weight force is pointed down, so that force is going to be negative. Now, the total force on an object is always equal to mass times acceleration. So, when I combine these two, I get the normal force of 3 on 2 plus the weight force of 2 is equal to mass times acceleration. The weight of 2 is easy to find. The weight of 2 is equal to mass times gravity, which is in turn equal to 2 times 9.81, which works out to 19.62 newtons. So that's the size of the weight of number 2. So normal of 3 on 2 minus weight 19.62, or if you prefer plus a negative weight, is equal to mass of 2, which is 2 kilograms, times the acceleration. It's not moving, so the acceleration is 0. So simplifying all of this term goes away, and we are left with the normal force of 3 on 2 is equal to 19.62 newtons, and this would be in the j hat direction. Now, let's look at the forces acting on the 3 kilogram object in the y direction. The total force is composed of the normal force from the table plus the normal force from 2 on 3, which is pointing downwards, and so that we'll later find that that's negative, plus the weight force, which of course is also negative. But total force is also equal to mass times acceleration. So we can say that the normal force from the table plus the normal force of 2 on 3 plus the weight of 3 is all going to add up to mass times acceleration. Now first let's find the weight of 3. That's equal to its mass, 3, times the acceleration due to gravity, that's 9.81, which works out to 29.43 newtons. So that's the weight of 3, that's the thing that we have to put in over here. But there's something else that we know. We don't know the normal from the table, but we do know that the normal force of 3 on 2, the force that book 3 was exerting on book 2, was 19.62 j hat newtons, which means that the force of 2 on 3 has got to be just the negative of that. It's just pointed in the opposite direction, an equal and opposite force, according to Newton's third law. Negative 19.62 j hat newtons plus the weight, which is negative 43 j hat newtons. All of that is equal to mass times acceleration. Now, the acceleration of this book is 0 because it's not moving. And the mass of it is 3, but it doesn't really make a difference in this case. So when you simplify all of this, we end up with the normal force from the table plus negative 19.62 plus 29.43. That's going to come to negative 49.05 J hat newtons is equal to 3 times 0, which is 0. So the normal force from the table is equal to 49.05 J hat newtons.
Another type of puzzle involves a spring. The stereotypical spring is a thin piece of metal that has been manufactured into a coiled shape. If nothing is pushing or pulling on the spring, in other words, if there's no force acting on it, the spring will maintain a length known as its natural length. But if something compresses the spring, then, unlike a rope, a spring will visibly shorten from that natural length. Conversely, if something stretches the spring, it will visibly lengthen from its natural length. In this course, we will symbolize the change in the length of the spring with the symbol delta x. Some books use the letter x without the delta, but our way shows that what is really happening to the spring is a displacement. As you probably guessed, the size of the displacement depends on the size of the force, but it also depends on the stiffness of the spring. A very stiff spring, like the one found in the shock absorber of a car, needs a much bigger force to compress it than the much flimsier spring that you would find in your ballpoint pen. The stiffness of a spring is denoted by the letter K and is known as the spring constant of the spring. This equation, which describes basically how a spring works, is called Hooke's law. Now, let's apply Newton's third law to a spring, the law of equal and opposite forces. If an object pushes down on a spring, that means the spring must push up on the object with an equal and opposite force. We can use this knowledge to our advantage in a question like this. A 15-kilogram object is at rest, suspended from a vertical spring with a spring constant of 1,200 newtons per meter. What is the elongation of the spring?
Let's start by drawing a picture. Here is a 15-kilogram object, and it is suspended on a spring like that. Let's represent this object as a spot. This object feels a weight force pointed down, and it feels the spring force pointed up. Now, how do we know that? Because this object is exerting a force on the spring in order to elongate it. But by Newton's third, the spring must therefore be exerting a force on this object. So we can represent the spring force like that. Here is the origin. I'm going to have it pass through this spot. And I'm going to set upwards as the positive y direction. So in the y direction, the total force is given by the spring force plus the weight force. But total force is also equal to mass times acceleration. So that means that the spring force plus the weight force must be equal to mass times acceleration. Now, weight is equal to mass times gravity, which is in this case 15 kilograms times 9.81 meters per second squared, which works out to 147.15. So the weight of this object is 147.15 newtons. And remembering that it's pointed down, that means that the spring force plus the weight force, negative 147.15, is equal to mass, 15, times an acceleration. Well, it's not moving, so the acceleration is 0. So this entire right side becomes 0, and we can tell that the spring force is equal to 147.15 J hat newtons. But we weren't actually being asked for the spring force. We were being asked for the elongation of the spring. So since we know that Hooke's law tells us the relationship between the spring force and the elongation of the spring, or let's call it in this case delta y, since it's in the y direction, then that means that we just need to use this value, negative by the way, take this value, 147.15, that's the force that the spring is exerting, that's going to be equal to negative k, which we were told was 1200, times delta x. So 147.15 divided by 1200 gives us delta x of about 0.12 meters. More correctly, it's negative 0.12 meters. So yes, this is how we figure out the displacement of the spring. The object has lengthened the spring, in other words, displaced it in the negative direction by 12 centimeters, 0.12 meters.
In this video, we illustrated 3 additional forces: weight, normal, and spring. We saw a puzzle that had 2 objects and therefore 2 free body diagrams. And we saw for the first time a case where some forces pointed in x and others in y. In the next video, we will introduce the force of friction.